So, so welcome everyone. This is a tutorial that we do in the context of ECP, the tutorial on template task graphs. I am Thomas Hero from the University of Tennessee, and I'm doing this presentation, this tutorial with Joseph Chouchard from the University of Tennessee. And that's a collaborative work with George Bozilka, Ed Valef, Robert Harrison, and Purnima Nokala. And I see that Ed is with us, so we are at least 3 people who can answer your questions on TTG if you have any. I hope the tutorial is quite interactive, so don't hesitate to stop me and ask questions. I assume because nobody complains that you can see my screen and you can hear me. If you want to follow their hands-on on the during the tutorial, if you want to follow them on your machine, you can go to this URL https://bit.ly ttg-tutorial, where that will send you to the wiki page, where we have all the material for the tutorial, and there are instructions on how to install Docker and then the Docker image and then the source for the tutorial. And we'll have about 10-15 minutes of introduction, during which, if you don't have Docker, I encourage you to install Docker. It takes at least that time. So TTG is a product of the EPEXA collaboration and the TSC collaboration before. That's an NSF funded project initially between ICL UTK with George Bozilka and me as CopyEye, and Joseph Chouchard joined us a couple of years ago. Then there is Robert Harrison from Stony Brook University and Ed Valef from Virginia Tech. The objective was to provide the better way to provide task-based application, to program task-based application for irregular algorithms and targeting, of course, distributed memory and large-scale machines. The goal from the beginning was to have multiple runtimes under it, with Parsec runtime that we develop at ICL being the one that targets high performance and efficiency, and Madness was the original runtime developed by Robert and Ed, and on which they have a lot of applications written already. The target applications are typically adaptive central spectral element calculus and block-round sparse algebra. That's the two type of applications that motivated many choices during the development of TTG. But the goal of TTG is to be a general programming interface for task systems. So if we look at the jungle of task-based programming interfaces, we can categorize them into 3 large categories. Maybe the interface you are the most familiar with is the insert task interface. That will be something like we do in OpenMP or StarPU. The idea is that you have a sequential task discovery, you have a sequential thread that will discover the task and expose on what dependencies or on what data this task depend. And that apparent data access order defines the directed acyclic graph of tasks. And then in the background, there are working threads that will take the tasks that are enabled at a given time because all their inputs are satisfied. All the tasks that they depend on have been executed, and this task can be executed by the working threads. Another approach that was maybe best illustrated with the C++ features of or Madness or HPX is continuation-based programming, where the programmer will define an object, a future, and then one task will set a future, another task will get the future. If a task tries to get the future before that future is set by the source task, then the scheduler will execute another work so that until that get dependency is satisfied. So in the insert task programming interface, the challenge is, of course, the sequential threads that defines the order of apparent data access order and what that defines the DAG. So these sequential threads need to discover all the tasks of the DAG, and that can be quite a long task for very complex operations. In the continuation-based programming approach, the issue is that the programmer has to define as many features as there are edges in the graph. And so these two limitations, we believe, limit the scalability. And one approach to remove that is to go to abstract task graphs interface. And examples of that are Dagger over Charm++ or Parsec PTG was an example of that, and TTG is one example of that. And the idea of an abstract task graph is that the programmer defines the internal representation of the entire DAG of tasks that is then executed during the runtime. And during the runtime, based on that internal representation, any thread can generate tasks. So that's what I try to say in this slide, that what's really interesting with abstract task graph representation, programming interface, is that the generation of the DAG itself becomes a fully distributed operation. So any threads can discover new tasks that are inserted in the DAG, and any thread, of course, can execute the task as in all task-based systems. There are other interests to task-based programming in general. So it hides the complexity of data movement. It allows the runtime system to adapt the execution to the machine instead of recoding the entire execution. Instead of recoding, so changing the code every time we change the machine. So let's go inside TTG itself. So a very high level overview of TTG. What consists of a TTG? So a TTG is like a graph like you have here on the top right. It's really a graph with cycles, okay? Here it's the DAG for a POTRF operation, for those of you who know dense linear algebra. And the tile view of the tile algorithm for the POTRF operation, we separated into four classes of tasks: POTRF, TRSM, circ, and gem. And then there are dependencies between these tasks here in the DAG of tasks that we see at the bottom. So the DAG of tasks is what is executed at runtime. But what the programmer will build with the abstract task representation is a folded representation of this DAG of tasks. The difference between the two is that folded representation here is always 4 task classes plus some other to help the composition, but it's always these 4 task classes, whatever the problem size. And then when we instantiate that abstract graph on a given problem instance, then we unfold it at runtime to build these DAG, and that DAG here on the bottom right will be dependent on the problem size and can become very large. That doesn't change the fact that the object built initially is of constant size. And so in TTG, that's the approach we'll take to describe the operation as a set of tasks by providing template tasks and then connecting them with edges to form a graph, and then unrolling that graph during the execution will generate the DAG of task and execute the DAG of task in parallel. So they are template tasks, and they are instantiated into tasks at execution. So one single template task can generate a large number of unique tasks, and a task is a template task plus a task identifier plus the input data for that task. Then we have terminals. Terminals are what allow us to connect template tasks together, and edges that connect template terminals together. And then tasks can do sends to instantiate a given edge. So as I was saying before, there are multiple backends to TTG, Parsec and Madness, and we are going to look at them. So I'm showing this kind of graph just to be clear. When I show a graph like that, a graph where a template task is 3 boxes on top of each other, that's a template task. That's not a task. The name of the template task is here in task A, but that's a template task. And there are inputs and outputs. The input terminals are marked at the top. The output terminals are marked at the bottom. And sometimes I put the type, sometimes I don't. And then we have edges connecting these terminals. And then we are going to build this kind of graphs. Okay, so what is the TTG execution model? It's an SPMD model, so all processes execute the same program. Of course, the program can, the code of the program can depend on the rank, so the user can do any kind of programming, but the model is SPMD. All TTG programs are MPI programs today, and so there is a concept of world which is similar to the communicator concept in MPI. And a world is used to query the number of processes in a rank, and it distributes the processes between multiple worlds if the user wants to define multiple worlds. They can be a single or multiple entry. So I'm sorry, somebody has a mic open. Okay, perfect. So there can be a single or multiple entry points into the DAG. And one or more processes can kick off the computation, by feeding information into the task graph, and then the computation and the communication will unfold in the background without explicit receives, at least. The programmer still do explicit sends to instantiate destination tasks. Worker threads will execute non-preemptive tasks that will eventually complete. And while doing so, it may discover new tasks and or fulfill the input data for existing tasks. There is a fence at the end of the application, ideally, or anytime the programmer needs to synchronize with a non-test based application to wait that all the computation initiated by the initial invocation complete. And then we'll see in the presentation later, in the tutorial later, how we can compose them to build a complex application. There is a TTG memory model. So the TTG runtime manages all the data fed into the DAG for the user. So the programmer will explicitly send the data on an edge to instantiate the tasks, but all the data is moved transparently. The send operation is the same between two threads, or between a thread and a device, or between a thread on a node and another node. That is the same send operation. The data is moved transparently in the background. There is no explicit receive. We have also the broadcast operation. We have immutable data and mutable data, and that is detected using the C++ language. So const L-value references argument are immutable data, and they are maybe shared between tasks. So we are going to avoid doing unnecessary copies. And mutable data, which are R-value reference arguments, so something with a T and a double ampersand in the prototype, will receive a private copy unless we can detect that it is safe to reuse the data because the source task has moved the data into the same task typically. So we have a few applications. We start to have a significant set of benchmarks on top, written on top of TTG. Is there a question? No. We have a few benchmarks written on top of TTG. So here I'm showing just to give you an idea of the kind of performance we were obtaining on large-scale machines with TTG. So we compare TTG with Chameleon, which is an implementation of the POTRF, the Cholesky factorization POTRF on top of StarPU, and we compare with dplasma, which is the implementation of the same operation on top of PTG. So StarPU is an inter-task paradigm. dplasma was also an abstract task graph programming paradigm. And you can see that the TTG implementation on top of Parsec scales as well as the dplasma implementation, in fact, a little better for very large runs. More on the target of TTG, we have a benchmark of multi-resolution analysis, where the DAG is really data dependent and very irregular. And so the state-of-the-art implementation of that benchmark was on Madness native, directly using the future or the continuation-based programming paradigm. So that will be the blue line in the graphs. And here we are observing execution time, so lower is better. And we have the two implementation of on top of TTG using Madness as the backend runtime or parsec. And with the parsec runtime, we get significant performance improvement compared to the native implementation on both machines where we evaluated that. And last, we have recently looked at the composition of operation at the high level. We'll talk a little bit about that at the end of the presentation. So we look at the performance of POTRI, which is a dense linear algebra operation that composes two algorithms, one after the other, TRTRI and IUM, and the composition can be much faster. So we compare that with Chameleon over StarPU, and we see that we get much better performance on the logarithmic scale here with higher beta is better for the performance. Okay, so I'm not going to go too much on the performance. The goal of the tutorial is to learn to use TTG. So let me go directly into the API. So that's the basic API for TTG. There are three categories of function or methods here. In blue, we have everything that allows us to describe and build the graph of template tasks, the TTG. And in red, we have the runtime operation. So the fact how to execute and how to start up the DAG of operation. So the main one that we're going to look at is make_TT. Make_TT creates a new template task with a set of input and output edges. Make_TT is a factory system. It provides it defines a new class and provides an object of that class that you can use to schedule. There is another more involved way to build TTGs, which is to derive the basic TTG-TT class. We are not going to show that. We are going to always use the make_TT in this tutorial. Inside the task itself, inside the function associated with a task, the user needs to instantiate destination tasks by calling the send operation. So there are three variants of that function: send, sendk, and sendv, because they can send data along an edge with the key and the value, or only the key or only the value. So we'll see in some examples when we use which one. Most of the time we use the send operation. Then when we build a DAG, we have the edge type. An edge carries two things. It carries a key and a type. The key defines, so if you remember what I said very quickly at the beginning, how do we get from a task template to a task? We take the task template and we give it a unique name by providing a key, and we give it the input data, its input data, and so this input data will be of type T for that edge. If I have three input edges, I will have then three different input data. So that's what defines the two template parameter of this TTG edge type. And then we have collection of edges to be able to pass them to make_TT as input or output edge for a given task template. At execution, we have make executable. So once we have built a TTG, we have to tell the runtime system that this collection of TTs that we have registered to now build together a template task graph that is executable, so that we can schedule on the worker cores, and that allows to do some optimization for communication, prepare some communication at that point. Then we can start the execution straight with TTG execute, and we can wait for the completion of a running graph with TTG fence. At TTG fence, all the tasks that are executing in parallel, so TTG fence is really a hard synchronizing routine. When we leave the fence, all the processes in the world are done executing all the tasks that have been discovered during the execution of all the registered graphs. And we can start up that execution with TT invoke. I will show some example. We have a convenient function, which is TTG print, which provides a pretty printing for the tasks. And in particular, it avoids multi-threaded garbled output So if you do two tasks, do TTG print, we ensure that the lines are going to be correctly separated. The main function of a template task is the function that we are going to execute when the task is ready to execute. So that is provided by a function object and typically a lambda that has a very fixed prototype. So, well, not a very fixed prototype, sorry. The prototype of that lambda can have a key if the task template instantiate multiple tasks. It has to have a key, and then it can take a const object reference if one of the input is immutable data, or a value reference if it takes a mutable data. So here in the third example, the task inside its body here can change the value of val and forward it to another task, or then use it, but it can change the value of val. And the runtime system knows that, so the runtime system will have provided a copy if that is needed, a unique copy if that is needed. We also have generic data, and Joseph will going to say more about that, because I am very slow, I realize. So let's go into the hands-on part of the tutorial so we can look at the first example. So the first alternative is to build your own programming environment with TTG. I'm not going to do that, so I'm going to skip that for now. I'm going to use the Docker. So you can, okay, of course. So you can get the Docker from Docker Hub under that name. I don't know if anybody has a problem until now. If you have, let me know. And then we can run the Docker with this command. So Docker run -it means interactive, -rm means that we are going to remove the container at the end of the session, so you don't have to manage them by hand. And then I'm mounting the current directory into this directory inside the container, so that will allow us to access the source of the tutorial.
Can you increase your font size a little bit?
I can. Well, that doesn't, yes. So that's the window that matters the most. Let me see if I can increase the font size. I hope now it doesn't work. Yes, it works. Okay. Can you see?
Yes, I think that's good. Thank you.
So I'm using VS Code because there is a nice container integration with VS Code. If you take the VS Code console, you can attach to a running container. And so here I attach to the container tutorial TTG that I launched in this terminal before. Okay, and so here inside this VS Code terminal window, I am inside the container itself. And if you have downloaded the source of the tutorial, we have created this ECP September 22 directory in which you have all the terminal. The first thing I'm going to do is create a build directory. And from that build directory, I can run CMake on the main CMake list at the top of the repository, and ask it to generate Ninja build file, because I prefer Ninja to make. And so that detects the installation of TTG and the compilers we need, and that prepares the makefile for our example. So if we look at the CMake list to compile TTG, so we need a pretty recent version of CMake, but that's not too recent. Then the main language, of course, is C++ for our project, and we just require the TTG package. And that should be all you need to be able to compile your TTG code. Then if I look at, yes?
There's a question in the chat.
Yes.
The Docker image does not seem to work on macOS ARM. Is that right?
Oh, yes. Okay, I didn't test on the macOS ARM. So it's possible. Sorry about that.
Okay.
Yeah. Okay. Okay, so let me continue on that. Just quickly an overview of the CMake infrastructure to build your TTG programs. You just define a new executable as with the set of sources here, and then we need to tell a specific target compile definition. As I was saying, there are multiple backends to TTG, and so you select the backend that your binary is going to use by defining if you are going to use parsec or madness with these definition variables. And then you just need to say that your binary links with the parsec version or the madness version of the TTG library in the target link libraries. So if I go back to the slide, the very first example is let's create a the simplest template task that we can. So I will call it TB. So how do we do that? Okay. So here I'm defining a new template task. We define a new template task with make TT, and the first argument of make TT is a lambda function that takes as argument the parameters of, well, the first argument will be the key of the template task. So in the example I want to do here, I will say that the task TB use int as a key to identify uniquely the task, and it doesn't take an input data. So it's very simple. It's just here I'm defining a template task that is instantiated by a unique ID of type int and doesn't take input data. I will say that when this happens, I will print which task is running, and that's all we do here. Okay, so that's the function of the template task. The template task needs to have input terminals and output terminals. Here, in this very simple example, the input terminals are empty and the output terminals are empty, so I don't need to provide anything. I need to provide a name for that template task, and I need to provide a collection of, well, a set of names for the input terminals and output terminals. That's mostly to help the debugging and processing. Once that's done, I need to say that this is all I have in my template task graph at this point. And then I need to define the, then I need to start the execution. So there is no input flow, there is nothing here. It's really an embarrassingly parallel set of tasks that do not read or output data. So it's very simple. And I can say that if in the world of TB, the rank is 0, so that I instantiate this task only from one process, of course, then I can invoke TB with the key 0 and other keys. Okay, so that should create two tasks, TB of 0 and TB of 1, that will execute when it is possible. So I need to set the runtime system on by telling TTG to start to execute things, and then I can ask TTG to wait that everything that is defined in the world of TB executes. And when this is done, we finalize TTG and we can return exit success. So if I compile, sorry, I should have compiled only this example. The example is diamond. And I made some mistakes, of course.
But I think you need to provide the type of the key as template parameter to make TT, because we can't infer it from the input edges, because there are no input edges. So it would be, yes, int. and then you have some only single colon for the namespaces for TTG edges right there.
Oh yeah, fence execute
fence and execute, and above in the TTG edges.
edges.
Oh yes, there. I think it's get world.
Make execute. I did that wrong too. Sorry.
Oh yes.
Almost there.
And I think it's get world. Almost there.
Okay. Make graph executable. Wow. Okay. And so now if I run that thing, so we have some warning issued by the runtime system because that's a failure of the Docker HWLock implementation. The HWLock library inside Docker fails detecting the number of cores properly, so I can set the TG num threads to the number of cores to really execute. And then the two tasks B of 0 and B of 1 are instantiated and executed. So now if I want to make this diamond example a little closer to diamond, what I want to do in the end is to have a task A that sends some data to two tasks B0 and B1, and then they send back the data to a task C. And to do that, I need to introduce three different type of template tasks and connect them with edges. So the first thing we do is define the edges. The first edge will go from A to B, and we have to give it a name. Okay, and when I do that, the edge from A to B targets a task template of type B, so it has to take a key to know which task to instantiate into the task template of B. So the first parameter, template parameter, is the type of the key that we target. And the second parameter is the type that is the type of the data that is carried by the edge. And here, for the example, I will just pass a double. So we can define an edge for A to B like that. And then I will define an edge from B to C. And we still carry double, but tasks of type C, since there is only, in my diamond example, a single type of type C, we can take no key for, we can not have a type of key for the task template of TC. So now if,
there's a wish that you maximize your VS Code window.
Yes, since I'm not showing anything else. Okay. So let's start with defining the task A. Again, I'm defining a simple diamond, right? So that the task template TA takes no key parameter. So that means that there is a single task instance that will instantiate the task template, of course. And it doesn't take an input data either. So it doesn't take anything. We are going to say that we are executing the task TA. And then we need to send some data and some key to the task TB. So the task TB will be on the first output terminal of my template task TA. So the first template output terminal is identified by 0. And task of type TB, as is denoted by the type of edge here, takes an int and a double. So I need to provide an int and a double. the first one is the key of the destination task, and the second one is the data carried by the edge, what I send to that task. So here, the task TA of nothing will send the value 0.0 to the task TB of 0. And if the task TB of 0 doesn't exist, it will instantiate it doing that. And I can do the same thing on the same output terminal. I can send another data on another task TB. Okay, how do we know that this is the task TB? Because here on the input edges, I have still nothing. TA doesn't have an input, but it sends the data to B. So in the TTG, in the edges that I'm passing here in the output terminal, I put the edge that is going to carry the message. I need to provide a name and then names for the output terminal.
So I should mention that the names are optional. You don't have to provide them. It's good for debugging and stuff like that. But
I will add a template task for TC here. So we are going to take the task task C, but this time we don't have a key, so the void here is correct. But we need to receive the two inputs if you want to make a diamond. A send to A and B, to B and B, B0 and B1, and then B0 and B1 send to C. So I need to receive two inputs. Sorry. And since I'm not modifying this input, I denote them as a const reference. So this is task C. I will display the two data I received, and then we don't need to send them to anybody. There is no input, there is an input edge, I will come back to that. There is no output edge. That's the class TC. And okay, so you say I don't need to define them here. So I don't provide the arguments, right? So there is an edge missing in this graph. We are going from A to B, so we need to say that now B receives data as input. Sorry, I didn't do any change to. I receive an input I, so this is task TB. It received the data that we received, and then we need to forward this data somewhere. And in the case of the diamond, it depends on the value of the key. So if key is 0, then I'm going to send on my first output terminal to the task C that doesn't have a key, so I don't need to provide the key, but I need to provide the data that I'm sending to it. And if k is equal to 1, then I can send on the second output terminal the same value. I was saying before when I was presenting the function that send has multiple variants. There is send v, and send key, and send k. When we are only sending a value, we use the send v variant, and when we are only sending a key, we send the send k variant. The parsing doesn't allow us to differentiate between the cases. We simply send. So B now has two things. It has an input terminal and an output terminal. The input terminal, I am connecting the edge A to B, and the output terminal, I'm connecting the edge B to C. And here in C, I'm connecting at the input terminal the edge B to C. So I'm building a graph with only three nodes, right? The nodes TA, TB, and TC, which are template tasks. And then these three nodes, they have a single edge going from one to the other. But at execution, because the task template TB has a key parameter K, it can be instantiated multiple times. So these edges will multiply in the DAG of tasks, and each send with a different key value here will instantiate a different task. And then we are merging them back in the BC case.
Don't we need two output edges for task B because we're sending
No.
on 0 and 1?
No, that we are sending, so it is the same edge in the template task graph. It is different edges. Oh, what I was saying. Yes, you're right. Sorry. Right, I'm wrong. Okay, so the error I made here is that because the task C has two input flows, it receives two data, it cannot have a single input terminal, right? It needs to have two input terminals. So if I do that, that's still wrong because this edge doesn't differentiate. So here, I cannot have an edge that connects to two input edges. It will send the same data. The error is here really in the definition of template task B. I said that I was going to output either on the output terminal 0 or the output terminal 1. So I need to define two output terminals here in the case of B. And so the two edges are different. They represent indeed the transfer from the output terminal 0 of TB to the input terminal 0 of TC and the output terminal 0 of TB 1 to the input terminal 1 of TB. So it's B0 to C0. And we have a second one, which is B1 to C1. Okay. So did I miss something else? So here now, we don't need to invoke TB directly. We can invoke TA on the rank that is hosting TA, and TA doesn't take a key. So TA is only invoked like that, and everything in the same world, but I can use TA everywhere. So now if I, this is wrong. Okay. If I compile this example, we made some mistakes. No parameters.
Yes, remove the closing bracket there. That should.
The closing bracket. Sorry, I'm not following what you are saying.
There's an opening. No. Where you just were with your TTG make TT.
Oh, sorry, I didn't say it's yes, sorry, and I didn't say it's a lambda.
Yes, right.
Okay.
So now it's a lambda.
It's the same issue with C as well.
It's the same issue with C because I copied C from the yes. Okay. Okay. And so if I run it now, we can see that trying to put this somewhere. Yes, you can see we execute the task A, then we send A send 0 and 1 to B0 and B1, and C will receive it. We receive the two data from 0 and 1. Okay. I'm trying to get back to the presentation, which is here.
I tried to fix some of the typos in the presentation.
In the
when you were
presentation.
typing.
Okay.
So
So that's a very simple. Okay, so we are here in the presentation. That's a very simple diamond example just to show how we can start to build a DAG. And I'm a little long, Joseph. I'm sorry. And we saw how to compile and how to execute that. Okay. So then I was going to ask you to try to extend that first example to become data dependent, where we want to iterate on the diamond. So the task TA will take as input a double value, and the task TC will output this out with double value and send it to the next iteration of the entire block until the task TC output a value superior to than a given threshold. So because I'm short on time already, I'm going to just walk over the solution here directly. So now already,
can you enter a presentation mode so it's easier to read?
So yes.
Yes, thank you.
So we have one more edge. We have one edge from CA to C to A. Okay, because we want to loop the data back to the A thing. We have each task now is taking at least one int because we need to know the phase of the iteration of the diamond that we are in. And so the tasks of type B now takes a special kind of key, which is not one int like before, but two ints, because we have the int of the phase and the int that says that this is the B0 or the B1 task. So that defines a new type of key. And when we define a new type of key, it's useful to extend to overload the operator double and inferior, so that on streams, so that the runtime system knows how to print the keys. It's especially useful for debugging information. So that is what we do here. So now I have these four types of edges, and all my task templates take an additional parameter. Well, they take the input value. Now we receive A that we are going to forward everywhere in the diamond. So the content of TA doesn't change significantly. We send always on the output 0, on the output terminal 0, but this time we send with the phase number either to B of 0 or B of 1, and then we send different value, A and A plus 1. That's just the example. The task TB now takes a pair as an input, as a key, and not a single value, but it still takes a single value A, and depending on the second parameter of the key, so here there is a mistake. It should be std get 0 of k. We will send to one output terminal or the other, so that we reach the task TC. And the task TC only changes here, and that's the part that start to be data dependent. So if the input value is lower than a threshold, then I will forward the data to my output terminal that is connected to the edge AC, so it's connected to the input terminal of the task template A. And otherwise, we terminate the execution by outputting the result. The rest of the execution is the same, except that now we need to invoke the task TA with a starting input value and a starting phase number. So I'm not going to run that example. It is in the solutions of the it is in the solution of the source under the diamond iterative data dependent. That's easy example. Okay, so I'm sorry, Joseph, I ate a lot of your time. You want to take the screen from here?
Sure.
Do we have any questions that?
Yes. So.
Okay.
Any questions?
So I'll stop sharing.
Yeah. I will share my screen. It's okay that you took longer. My voice is not so good today, so okay. Let me just remove the chat window here. So okay, and remove this. How do I? Okay, that was okay. So yeah, I'm gonna talk a little bit about more extended or advanced features of TDG. I do have some hands-on parts. We'll see if we can get through them. Maybe I'll go through the features first, and then if we have time, we can go through the hands-ons. One thing that Thomas already hinted at is that you can have custom key types. In his example, he used just a std pair, and we support we support TDG supports std pair out of the box. If you create your own key type, like you see on the left side here, then there's two things that you have to define in order to make it work with TDG. One is they have to be equality comparable. So just overload the operator equals, and yeah, check that the two keys are the same. And the other one is that they have to be hashable. And for that, we look for a member function called hash, and that should return a size t. And you can do whatever you want with your key data. Just hash it down to 64-bit on a 64-bit machine. And that we use that hash in order to track tasks that have the same key. So in the end, there's a big hash table in the backend that we use to keep track of tasks. So it's always a good idea to have a good hash function there. It doesn't have to be cryptographic, but try to avoid conflicts. The parsec backend will warn you if there are too many collisions. There's a hash table that grows in steps, and at some point it will give up growing and just say that there's too many collisions. So at that point, it's good to revisit your hash function. The other thing that is interesting for the first example is that you can fuse edges. So it comes in handy to be able to have two different edges as the input to the same input terminal. So in this example here, we basically have a recursive task A that typically receives the data from its own. But for the first invocation, we have an init task that maybe feeds some data into the into task A. What we do then is we have these two edges, and we call TDG fuse, which gives us a new edge that combines those two edges, and we can pass that edge as input terminal. You can also pass it as output terminal or output edge. In that case, if you send on that terminal, you will send along the two or however many fused edges you have. So that is an important tool for building more complex task graphs. So now I have a hands-on here. How much time do we have left? We have half an hour. So we have, let me go to that example. Yes. I'm sorry, that was not what I wanted to do. So we created an example for a 1D stencil where basically there's one we chunk up the domain into cells, and each task updates a cell and then sends its left and right neighbor to the neighboring cells. We have 3 tasks: init, update, and result task. In the result task, we can print whatever we computed at the end, or put it into a data structure when it eventually comes out of the task graph. So the first task here would be to add the calls to ttg send to the task. Sorry, to the code. The code is in, if you downloaded the tar archive that's in the wiki page, I think we also have it in the Docker container.
Yeah.
There's a directory called stencil and a directory called task1. And if we look at the first task here, it's a little more involved in the diamond. So we have the custom key structure that I mentioned. We have some command line parsing and the function that computes the cells, command line parsing, and then we have an init task here where we take the ID of the cell and create the cell. So we allocate a new cell, allocate the borders left and right, copy from the cell into the borders, and now it would be the task here to add the send calls, and then we do the same in. I can go through the rest of the code just to give you an overview. So there are no input edges for the init task because we will invoke it directly, and there are 3 output edges. One is to the left, one is the next cell, and one is to the right, of course. And then we have the update task that basically computes the next step of the cell. And if we are below the threshold of the number of steps that we have defined, then we send the cell and the boundaries to our next task and the neighbors. And here we use the fuse, TDG fuse, in order to fuse the init task that sends the initial boundary and cell, and the edge that comes from the update task itself. So here's this recursion that we saw on the previous page. And then there's the result, and the rest should be known by now. You've seen that before. So let me, if you want to follow, if you don't want to code it yourself, there's a directory solution here that already has the solution. I will just try to quickly put that together here. So we will send to our left neighbor our left boundary, and of course the key here is, which you see, I put a hint in the slides so that I don't have to think about how to compute the neighboring cell, because it's we wrap around the edges just to make it easier. And then we move the left boundary, and this is for, actually it should be 0 because it's the first step from the init task, and this is simply our position, so X and the key, and this is the cell, and then we send to the right. Of course, this has to be 1, and this has to be 2. So 0 is the init task to the left. 1 is the init task to the cell itself, and 2 is the init task to the right. And then there's no case. Is that right?
You just gave this one.
Yes. +1, right? So that's correct. And then this should be my right. Okay.
And you put 2 plus. There are 2 pluses on this line.
Oh, how did that happen?
You're good.
Thank you. Okay. So this is how we would send from the init task to our neighbors. If we do the same in the update task, here we would instead of step 0, we would use the step that increment the step that we're in right now, and we have to use the key.x because here the key contains both the step and the position of the cell. So this is what it would look like in the update task, and that's all we have to do for this task. If we compile this, let's see. Sec. I hope it compiles. There is a set of parameters if you want to play around with the size of the domain, and you can print the dot of the graph and plot it if you want to. All of that is we say and so task 1. So we take the time, how long it takes to execute. If we pass that -h, we see that we could enable printing the dot, so we get the raw dot output that we then have to pass to graph this. Let me see if I still have that here. I do not, but I can quickly generate that. This is correct. So this is what the task graph would look like. I should note that the left always sends to the left neighbor, but it's right input. So that's why these arrows here, the edges cross. And of course, the cell output itself sends to the cell input. And eventually everything lands into the result task. Okay, so that would be the first task. I have 20 minutes left. I will just go over I will skip over the rest of the hands-ons probably, and just talk about the features that we have so that we stay in time. Okay, here we go. Okay, so another feature of TTG that excuse me, that is useful is process placement and priorities. By default, all the tasks have the same priority, and if you don't provide an explicit process placement, TDG will use the hash to the hash of the key of the task to map it to a process on which it will execute. Usually that's not a great placement, so you will end up with much more communication than is optimal. So in our example here, okay, so the way we control the mapping to processes is by providing a lambda that returns the process of where we want to map our key to. In this case, it would be the X member that determines or helps us determine the process. And we also can provide priority maps, which are useful for some algorithms, especially in linear algebra. And in the simple case here, we would just take the Y member and return that. And priorities can be any positive integer. So you have a wide range that you can work with there. In the stencil example here, we would define the key map such that we take the position here. So this is for the init task. If it was for the update task, it would be the X member of the key. And we would try to give each process a consecutive range of cells, so that only at the left and right, at the very left and right border of this pack of cells, we actually have to send cells to our neighbors. I'm going to skip over that here. So this is what it would look like. We have 2 cells in one process, 2 cells in the other process. If we didn't do that, it would probably we would probably end up with the first cell on process 0, the second cell on process 1, and so on. So right now, TDG doesn't have a notion of load balancing in that way. In some intelligent node balancing, where we actually look at the load of processes, it's more of a round robin, but that's not very efficient. So I always recommend providing a process mapping. It is also important to point out that we use constants in C++, especially constants of arguments, and the move operation to track copies that flow through the graph. So each object that is moving through the DAG is tracked by TDG. If you send an object to multiple successor tasks, and they're only consuming it, not mutating it, they will receive the same copy, and it will be the exact same data. So we try not to create copies if we don't have to. And the way we identify that is through constness. In this case here, we have to create a new copy because it's not const. So A is not const. Here we have to create a new copy because A might change, and indeed it does. So A is being reset and then sent again. So this creates a new copy. Here we don't create a new copy because you're moving it into send. So you're basically telling us that you give up the ownership of A, and we're free to handle it from here on out. The same here, since A is const, you're not allowed to change A. So if you can send it multiple times, and we can reuse the same copy over and over again because you promised not to change it. And then here, this is an object that is created on the stack, even though you're moving it into send, since it's on the stack, it might get lost after the task finishes. So we create a new copy that is then fed into the task graph. But if you move it, and depending on the data structure, if it's a vector, for example, we only have to create a hull, and we can move the content of the content of the vector into our new vector. So we're making full use of move semantics in C++. I will skip that. That's another exercise that we can come back to if we want to at the end. Serializing custom types. So imagine instead of moving a vector through a std vector through your task graph, you have a more complex data object that has multiple members that you want to move. So the first way to do that is to pack it when we have to copy it from one process to another, and for that we're using one way to use is the Madness archives. There's a similar API from Boost that we're using. I think they're quite similar. It's just mostly a different name here. But what you do is you feed your metadata, so the rows and columns and what have you in your matrix tile that we're using here, into the archive, and then you copy the elements of the data into the archive. Now all the whole matrix tile is in that archive. TDG will send it to another process, and at the target process, we will call load that you provided here, and you can unpack the matrix tile from the archive. So you would unpack the rows, columns, and the leading dimension, create a new matrix tile, and then unpack the data content of the tile. We also support broadcasting data. If you have a data object that you want to move, like here, and you have multiple receivers or multiple tasks that you want to send it to, it's better to use a broadcast than individual sends, because in the broadcast we can look at all the receivers and, for example, send the data only once instead of 6 times here in that case. And we potentially can save a lot of copying that way. So in that broadcast here, we would send on to 3 tasks on one output terminal and 3 tasks on the other output terminal. So as soon as you want to send to multiple output, want to send the same data on the same edge to multiple succession tasks, we recommend using broadcast. And as you can see here, you can broadcast to any number of output terminals that you have defined for your task. I should have swapped these slides. I'm sorry. This is not quite educational. Instead of packing your data into an archive, which always means that all the data has to be copied, then put on the wire, and copied out again. We have a mechanism for zero-copy data transfers where we copy directly out of your object into a new object. And what you do to use that feature is overload the TDG split metadata descriptor with your type. In this case, again, this is a matrix tile. And you have to implement 3 functions. One is get metadata, which returns some object that contains the metadata of the tile. As we've seen before, that can be the number of rows, columns, and the leading dimension. Here, all nicely wrapped up in a small structure. And a function called getData, which returns an IOVEC or an array of IOVECs that basically tell us where to take the data from. In this case, it's just one place, so one data range. You could have 2 or 3 that you need to transfer in order to transfer the type. And then at the target, we give you back the metadata, and you return a tile to us. You create a new tile with the metadata, and we will ask again for data. So the same play here, and then TDG is able to copy from the vector of the source into the vector of the target, and we don't have to pack the whole vector or matrix tile, what have you. So that is useful for improving the communication overhead. I think we've already seen a slide in the beginning about generic task arguments. What's important is that we use auto ~, so the right hand, what's it called? Right hand.
The R value reference.
Oh yes, R value reference for mutable arguments, like here for A, and simply an L value reference for immutable or const data. The reason we do that is that we actually put in a lot of effort to auto detect what your generic arguments are. And it turns out that if you mark it const, everything can bind to it, and we cannot distinguish between an R value reference and a const or a mutable argument and a const argument. So auto & is the way to go for a const argument. Right, and we recommend not mixing generic and concrete arguments. So if you use generic arguments, use them for everything. We will infer the type of the arguments by looking at your edges, because the edges contain the concrete type, and the lambda will receive the concrete type of that object that we pass into it. This is now might be a little overwhelming, but what we're trying to show here is how you can create your own, or how you can create a whole task graph and return it from a function that can then be used to compose task graphs, multiple task graphs, into larger task graphs. And what you would typically do is in your function that creates this task graph, you take an edge as an input edge. So in this case, it sends a double without a key because you don't know what the key would be. You just keep feeding doubles in here, and there's an output edge that eventually a double will fall out of your task graph. And then you created this patch task that takes the input that comes from the outside and dispatches it to whatever internal computation you're doing in your task graph. Then I'm sorry. Yes, you're creating a vector of template tasks that are connected through internal edges that the outside world will never see, and you call make TTG instead of make TT. Provide us with these the vector of TTs, and now we have a full-blown TDG that we can connect to. And I think we have an example here. Yes. So this is, you've seen the numbers, the comparison with Chameleon in the beginning. where we showed the performance measurements of the composition of POTRF and LAUUM, I think. This is the composition of TRTRI and LAUUM. And as you can see, the only edge that is really exposed here is the output result edge. I'm not sure how. Maybe Thomas can help me here. He wrote the code.
Yes, sorry. So so there are two output results, output terminals. One inside all the tasks of TTR, TRTRI, and the other in each task of LAUUM. And if you look at the code on there, so we define POTRI as a TTG. So TTG is a function, and we are going to return the make TTG. And we take the matrix as a parameter, but just to know the things like size of the matrix and type of the element and things like that. And then there is a generic input edge and generic output edge. That's the parameter to how to make a POTRI operation. The only thing we need to introduce is an edge, an internal edge between the TRTRI and the LAUUM. So that's the goal of the TRTRI LAUUM edge that we define at the line below. And then we just instantiate two TTGs for TRTRI and LAUUMs. Defining the ops in and out is exactly like for the slide before. And the only trick is that the output edge of TRTRI, so the third argument of TRTRI TTG, is this internal edge. And that's the input edge of the second TTG. And so we created a third TTG by composing the first two, by just introducing this hidden edge between the two of them. And then we return a new TTG out of that. And that builds a TTG that is the large graph that we see above, but the composition at the runtime level is at the granularity of the tile, right? So as soon as TRTRI is done from any task with one of its computation, it forwards it through the TRTRI to LAUUM edge to instantiate a dispatch task from LAUM, and then that is sent inside the TTG of LAUM. So there is complete overlap of the execution of the two DAGs.
Okay, thank you. I couldn't have done it better.
I think your voice needed a break.
Yes. We only have a few slides left, so I can probably go through that. One of the things that TDG partially supports and that we're still working on to finalize at this moment, so this is more, now we're coming more to sort of an outlook here, is pull terminals, where the idea is that instead of waiting for data to be pushed into your task, you go to your predecessor and ask for your data. So you're reverse traversing the graph, and it can be only one step, it can be many steps, but the idea is that we avoid pushing too much data onto other processes, for example, discovering too many tasks up front, instead asking for data once we need it. And it can be either greedy, so once the task is created through a push creation or through a push input, we will ask for the data, or it can be lazy. When all the other inputs are available, then we go and ask pull for the data from the predecessor task. That is still work in progress. What exists today are streaming terminals. It's basically a reduction on the input of a task. So you provide a reduce operator that will take an input and combine it into an already existing object that you can, it basically folds all the inputs into one input, and you can tell us either statically how many inputs there will be, or dynamically, say, now I have received all the inputs that I need, and then the task will be invoked on that folded object. In principle, TTG provides the concept of worlds. We've seen that on the previous slides. Each process has a rank in a world, and you can query the size, which is the number of processes in that world. Eventually, what worlds will do is partition the set of processes, and you can create task graphs that operate on subsets of all your processes, and you can still compose them so that different tasks, different subsets of these processes can talk to each other through edges. This is we're only missing the process set management at this point, but the concept of a world is already there, and you will see it once you start working with TTG. You will most likely start just working on a single world, which is the default execution context that provides the rank and size. I have 1 minute left. We have, as I've shown you before, we have these, we can generate these task graphs here. If you run with the Parsec backend, we can also provide you with the DAG that is unrolled when you execute your application, so that you can look at how much concurrency there is in the DAG. And we can also generate OTF2 profiles, which you can feed into Vampire to get such nice performance graphs here. So this is basically a Gantt chart of the tasks that are being executed. On the top here is TTG with the task graph composition. On the bottom is if we were to execute the 3 operations that are composed on the top, just execute them sequentially. So you can see that the composition has a significant benefit if you do that. As we've tried to convey in this tutorial, TTG provides scalable task graph discovery. The compact representation of the abstract task graphs removed some of the complexities that other approaches face at execution time. And the composition of subgraphs enables synchronization-free execution, which is comes in really handy for some problems. Someone asked for GPU device offloading. We're working on that. We hope to get this done by the end of the year or early next year. We need to finalize the pull terminals. We think that this is really useful, but it's only in a branch right now. And then we're working towards our first official release. And that's all we have. Any questions? I think you're right on time.
So one slide I skipped by mistake that would have been more useful if people were doing the hands-on, but I think the time was very short to do that. There is a slide that explains all the features we have to simplify debugging. So I will send you to the presentation for that.
Oh yeah, we skipped that, I remember.
Yeah.
I hope people could read my text. I forgot to increase the text size. I only see Orion's comment right now. Sorry about that.
I have a question. This is awesome. Sure. TTGs are a very C++y version of instantiating task graphs where you have vertices, you have edges, you define them all. The previous parameterized task graph, PTG, was very similar in the sense that you have, instead of edges, you define like state spaces, I guess, and you move between them. What are the advantages and differences between these two things?
So the major difference, and that was the motivation for creating TTG, is that the DAG instance, the DAG you unroll, can be completely data dependent in TTG, and it's very hard to do that in PTG. In PTG, you need the receiving task needs to know why it exists in a way. It needs to be able to compute if it exists by itself without knowing the data. In TTG, we remove that problem. So in TTG, you do the send inside the body of the task during the function that implements the task. And that send operation is the one that instantiates the successor task.
I think another big issue is that PTG, the implementation vehicle, was a domain-specific language. And here the goal is general purpose computation. And so therefore you need to have a native, some sort of a general purpose language. So C++ provides that. Also gives you composability. So instead of, we can reuse pieces as Joseph showed, that you can actually combine things together and stitch them together much more easily.
That's a fair point. One of the things, when you write a PTG, you have to build your data structures on top of what Parsec calls data collection. And so you have to port your data structures on top of that. The data collection is pretty generic, so it's pretty easy to do, but you have to do it. With TTG, you can work with any STL structure. You don't need to, or any structure you want to define in C++. We work with your object. We use the strong typing functionality of C++ to work with your object and not ask you to make it fit in an API that we specify.
Okay. So you did though have composability in PTGs, right? That existed.
Yes. Yes.
Yes.
It was limited though, right? And it needed a bit of a handstand to make it work.
Yeah. So
I understand TTGs are much more abstract, and the fact that you can dynamically move data, create tasks is definitely a big plus. Thanks.
Any other questions?
Okay, so if there is no other question, there are plenty of hands-on to try in the Docker if you want. You have our mails. Don't hesitate to contact us. We'll be happy to talk to anybody who wants to try stuff in TTG.
Thank you for joining.
Thank you.
Thank you. Thanks.
I am.